I'm Sean Gregory and I'm a PhD student at the University of Nottingham. I'd like to start by thanking the organisers of Tabletop Scale Cosmology 2025 for putting on this conference and for giving me the opportunity to talk about my research in the area of analog cosmology. The work of myself and my collaborators is to use the methodology of analog gravity to study the creation and subsequent thermalisation of matter in the early universe. First, I'll briefly cover our general research approach, followed by the cosmological theory to which we apply it. Then I'll discuss our experimental setup and the recent advances to what physics we can resolve. I'll talk about our most recent findings in the areas of non-equilibrium physics and fluid dynamics, and then finally I'll discuss in more depth the link between our experiment to cosmology and what we can hope to learn. So the methodology of analog gravity is to take a target system, typically something very difficult to access, and then to construct a different experimental system that contains the same key physical processes. And this is done in order to simulate the target system. So the typical example is that of a black hole. This is an object that we have very limited observational data for, and it would be very unsafe to play around in a lab with. And in the 80s, it was pointed out by William Unruh that the same physics of a black hole also occurs on the surface of a draining flow of water. And so a lab-based fluid dynamics experiment can be used to observe and study the phenomena predicted to occur around black holes, such as, for example, superradiance. Analog gravity is the specialism of the gravity laboratory here at Nottingham. So this is the team here from the gravity laboratory. We have myself, my colleagues Silvio Sciattarella, Vitor Barroso, Silke Weinfertner, and we're working closely with the theoretical cosmologists Anastasios Avgoustidis and David Kaiser. And we're working to apply this approach of analog gravity to the study of early universe phenomena. Our focus is on the reheating and thermalisation of matter fields immediately after inflation. And in this presentation, I'm going to be focusing mostly on the work from our most recent paper, which is cited up the top. The specific target system that we consider is a matter field undergoing exponential particle creation as a result of cosmological preheating. We consider a single field inflationary model in which the universe's quasi-exponential expansion is driven by a single field called the inphoton that slowly rolls down a near-flat potential. Inflation ends once the inphoton exits this slow roll regime and then harmonically oscillates around a potential minimum. This oscillation provides periodic forcing to the matter fields to which it's coupled, which results in an exponential amplification of the matter field excitations in a process known as parametric resonance. This amplification creates particles at a particular momenta, which depends on the frequency and the amplitude at which the inphoton field oscillates. As more particles are created, the nonlinear scattering processes between them become increasingly relevant. So this excites particles at higher momenta, which changes the overall momentum distribution until a steady state is reached, be this a thermal distribution or a turbulent energy cascade. So the specific toy model we consider is one of these matter fields in isolation, which we take to be a 2+1 dimensional scalar field early in the reheating process, such that the inphoton field has not yet had a chance to decay significantly. The experiment we use to reproduce this physics is a periodically driven two-fluid system. We fill a small cylindrical vessel with two liquids, an aqueous solution of potassium carbonate and distilled water, and an organic solution of ethanol and distilled water. And these separate out to form an interface between them. The vessel is mounted to a platform that shakes up and down to exert a periodic forcing on the fluid interface. We have a high degree of control on the amplitude and frequency at which we oscillate the system. And underneath the vessel is a checkerboard pattern, which we record through the interface with a high-speed camera. So waves on the interface distort the recorded pattern, and the exact spatial profile of the interface can be reconstructed at every frame of the recording through a technique known as Fourier transform profilometry. The core observable is the height of the fluid-fluid interface as a function we call xi that's a function of space and time. We describe the interface as a sum of individual wave modes by decomposing xi onto a basis of spatial eigenfunctions chi mn, and these each have a time-dependent amplitude xi mn. The spatial profiles are determined by the geometry and the boundary conditions of the vessel. In our system, we identify each mode with two labels, m and n, and we show the first few of these down the bottom here. So these modes are order m Bessel functions with n0 radial crossings. Since the basis is orthonormal, at any given moment in time, we can extract each mode amplitude from the data of xi by taking a spatial inner product with the corresponding spatial eigenmode. Repeating this for each frame of the video recording lets us measure the full time evolution of each wave mode. So now let's take a look at what we find. From flow K theory, we expect a significant amplification of those wave modes oscillating in a narrow band around half of the driving frequency. The finite vessel size discretizes the basis of eigenmodes, and so only one of these modes, that we call the primary mode, falls within this band. The other way in which we tune our experiment such that only the primary mode grows due to parametric resonance is to ensure that the driving strength is not large enough to overcome the damping of modes at higher harmonics. By driving at a frequency of 6.2 Hz, we excite a primary mode at frequency 3.1 Hz, which in our case is the one labelled by m equals 4 and n equals 1. We observe this primary mode to grow at an exponential rate that's also predicted from the flow K theory. Once the amplitude of this one primary mode is high enough, the nonlinear interactions with a few other modes also become strong enough to excite these also. We call these modes that are excited by the primary the secondary modes. As the secondary modes grow, they also excite modes at higher wave numbers, which in turn excite many more modes at higher wave numbers still. Through these interactions, the energy injected into the system at the wave number of the primary gets transported to higher wave numbers, i.e. smaller length scales, until it becomes dissipated by viscous dissipation. And this is what we see, energy going from one to few to many modes on the interface. Eventually, the primary mode reaches a high enough amplitude such that its interaction with itself becomes large enough to halt the growth. At this point, the energy coming in through the driving balances the energy flowing to higher wave numbers and that lost to viscous dissipation. All other modes stop growing very soon after, and a non-equilibrium steady state is reached. We see that in this steady state, the power spectral density across each excited mode follows a power law in wave number k. This is known as a spectral energy cascade. And since energy is injected into the largest length scale of the system and flows down to the smaller length scales, it is specifically a direct energy cascade. To model the intricate nonlinear dynamics behind this cascade formation process, we adopt a field theoretic approach. We use the Lagrangian at the top here for the amplitudes of all of the wave modes. The coupling coefficients f, g, and h can be calculated from spatial integrals involving the spatial profiles of the eigenmodes involved in the interaction process. So this tells us the permitted interactions, and so we can predict which mode should become excited by the primary. So for example, this interaction process here between two of the primary and one m equals 8 and n equals 2 mode is a cubic order interaction. In our most recent paper, we verify that this Lagrangian gives an excellent description of our system. Numerically calculating the coupling coefficients between modes gives us predictions for which modes should and shouldn't be excited. From the modes we observe to grow, we see that this is indeed the case, and furthermore, we can quantify the interactions between specific modes using connected correlation measures. and these verify that the modes are growing due to the specifically predicted interaction processes. We find that each interaction process conserves the frequency of the modes involved, as well as the label m, the azimuthal number. And we also find that the third and fourth order interactions are the only ones that are relevant. So this means that while in principle the full Lagrangian can contain nonlinear terms at every order, we can truncate after the fourth order without losing any predictive capability. We can even track the interactions through time to see when they become relevant. So this is very cool in itself, and we've learned a lot about fluid dynamical systems and the formation of spectral cascades. Typically for fluid interfaces, wave interactions and spectral cascades are considered from the approach of weak wave turbulence theory. The results from our correlation measures have verified two key assumptions of weak wave turbulence. The first is that of conservation of frequency, and the second is that wave mixing processes higher than fourth order can be neglected. So furthermore, weak wave turbulence theory only makes predictions about spectral cascades in the theoretically idealized limits. The finite size and the strong forcing conditions of our system are beyond these limits, and so it shows that the phenomena of a spectral cascade is more robust against theoretically challenging conditions than had previously been appreciated. But I know I'm talking to an audience of cosmologists rather than fluid dynamics researchers. So for the rest of my talk, I'll be trying to convince you why you should be caring about our fluid dynamics experiment. So while it's fantastic that we've been able to make these findings about fluid dynamics, our experiment was not originally conceived for that purpose. Instead, all of this work has been to establish a platform for analog cosmology experiments. Let's now look at how our experiment is able to simulate the model of cosmological preheating that I started the talk with. The analog is the following. The two-fluid interface is the analog for a massive field in the early universe, and the shaking platform serves the role of the coupling to the inflaton field. In cosmological preheating, parametric resonance is induced in the massive field by periodic forcing at amplitude A and frequency 2 omega naught, and the same is true for the fluid-fluid interface. This causes an exponential growth in excitations at frequency omega naught in both cases. In the cosmological case, this is interpreted as the rapid production of particles at a particular momentum scale k, and in the experiment this corresponds to the growth of a wave at a particular wave number k. As the amplitude increases, scattering processes cause the growth of secondaries, which appear as spikes at higher k in the power spectrum. Energy flows through the channels provided by the nonlinear interaction processes, and this acts to broaden the power spectrum until eventually we reach a steady state. And in our case, and in some theoretical models of cosmology, this state is a direct energy cascade characterized by a scaling law. This isn't just a qualitative comparison. We can write down an exact mathematical mapping between the Lagrangian of our experiment and that of certain models for cosmological preheating. Now I'll give a quick flavour for how that works. If one takes a general Lagrangian for the matter degrees of freedom in cosmological reheating, and then specifies that we only have one scalar field in an FLRW spacetime, then after a conformal transformation, we can write this Lagrangian in the form here at the top of the slide. Here, V is the potential and G is the field space metric, which makes the kinetic term non-canonical for theories that are non-minimally coupled to gravity. We can compare this to our fluid Lagrangian by expanding the field in terms of modes. If the field space metric has a term proportional to unity, we keep the canonical kinetic term present in our Lagrangian. If it also has a term proportional to xi squared, then we obtain quartic coupling terms of the same form as those in the fluid Lagrangian. This corresponds to a wide class of cosmological theories, but of particular note is that of Higgs inflation models, where the standard model Higgs field is what serves as the inflaton. In our fluid Lagrangian, we also have a cubic coupling term, which isn't very common to see in the typical models of preheating that are studied. Fortunately, though, this constant in the fluid Lagrangian is proportional to the difference between the densities of the two fluids. And so by adjusting the experimental parameters of the system, by making these densities very close to each other, we can suppress this cubic coupling term in order to better model many theories of preheating. So we are currently in the process of taking various models of preheating and then mapping them precisely to our experimental parameters, such that our experiment can function as a simulator for these theories. The highly nonlinear physics involved in these scenarios are very computationally taxing, even for state-of-the-art lattice simulations. And so the hope is that our experiment will be able to supplement these computer simulations and be able to simulate various cosmological models. So what is it that we actually hope to learn about cosmology through our analog experiment? Well, the first thing is about the scaling laws of the spectral cascades that form. We want to investigate how the spectrum changes as a result of different parameters, be they the experimental parameters of our system or physical constants in a cosmological theory. The second is that of timescales. How long does it take for the cascade to form? For this, we actually already have a prediction. We are able to predict this in our system by use of a reduced dynamics approximation. And with this, we can very accurately predict the amplitude at which the primary mode saturates. This value predominantly depends on the driving strength and the quartic self-coupling constants of the primary mode, though there's also a contribution from the linear damping and the frequency detuning. Frequency detuning is the small mismatch between the dispersion frequency of a mode and the frequency at which it is being forced. So since we may also predict the growth rate of the primary mode from flow K theory, we have a simple formula for the time that it takes for a system to reach the steady state from some initial amplitude. In principle, this reduced dynamics approach should be applicable to any narrowband resonance system, and we are currently extending it to other far from equilibrium systems. So at the moment, we're looking at the instability that occurs due to confined superradiance around a black hole, known as a black hole bomb. We are also applying it to various models of cosmological preheating, and will use our experiment in conjunction with lattice simulations to verify these predictions. So hopefully from this talk you are now familiar with our analog cosmology research. We study the rich nonlinear dynamics on a fluid-fluid interface and the direct energy cascade that emerges. By modeling these dynamics with a field theory approach, we can establish a mathematical mapping between the Lagrangian of our theory and to that of various models of cosmological preheating. The complexity of the nonlinear interactions within our system make it difficult for a complete analytical treatment or even computational simulation, but we can use our experiment as a physical simulator to probe this challenging regime. So thank you very much for listening, and thanks again to the organisers for putting on this conference.